Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is a continuation of a lecture on functions for intermediate algebra. I've actually added a part here. If you're looking through or watching through all of these lectures, you'll notice that we did start with part A, which is determining what a function is and what's not a function. And then we moved on to part B, which was all the ways we could represent functions, and part C, we talked about function notation and evaluation. In all three of those parts, we were talking about domain and range the entire time. Part D, which we just finished, was about graphs of functions, specifically about how to plot graphs of functions given a function in function notation, like f of x equals something. We also talked about how to use the graph to determine the function values at given points and also to read a graph. I decided to add in this part E, which is base graphs, because really I wanted to separate it out. I was going to include this in part F, but it'd be nice to actually separate this out into its own lecture. Base graphs is kind of a broad statement, and but basically all it means is that there are prototype graphs that we're going to manipulate in the long run, and so we're going to learn all these prototypes first, and then manipulate those to make really unique graphs later on. So let's go ahead and list out some of the base functions here. We're not going to list out their base graphs yet, but we'll talk about the base functions. Notice that I call it the base functions, or sometimes I will call them the parent functions, because from those you get all these, these child functions. But more often than not, I will call them prototype functions, because they are the prototype for the exemplar functions, the ones that give you the best examples of their functions. So here's what I mean. We have one that is f of x equals x. So that's the linear function. And what do I mean by the fact that this is a base function? Is that you could have some other kind of function, let's say g of x, that's just a subtle manipulation of this function. So it might be 3x plus 1. When you peel off all the numbers, that's just x. So the basic or the prototype function for this is y equals x. And then we're just attaching a 3 onto the x and adding a 1 on the outside of it. So those do very specific things. The next most basic prototype function, and maybe I'll go through, I'll keep it f as well, actually. F of x equals x squared. That's either a quadratic or a squaring function. I like to call it a quadratic function, but it is also known as the squaring function. Let's see, we went from a first power to a second power, so let's go to the third power here. F of x equals x cubed. That's known as the cubic function. And now we really don't move on from there. We don't do x to the fourth or x to the fifth, because honestly, a lot of our functions can be derived graphically from these three, for polynomials, that is. So instead, I'll take a look at other types of powers, specifically rational powers, or in other words, roots. So f of x equals the square root of x. That's the square root function. And then just like we had a squaring function and a cubing function, we have a square root function and we have a cubed root function. So f of x equals the cubed root of x. So that gives us, what, 5 functions? There are going to be 3 more that we're going to concentrate on in this lecture. However, I have to mention that there are quite a few base or parent or prototype functions out there. They're just the basic function for their type. And so when you get into trigonometry, you'll find there's a few more parent or prototype functions there. But these ones that we've listed out so far, plus the additional 3 that I'm about to put down, are really the ones that we encounter the most in algebra. So the next one will be the absolute value function. F of x equals the absolute value of x. And that has a very nice form to it. We'll talk a little bit about that when we go into graphing it. The last two, in my opinion, tend to be the most complicated of the group. You have what's known as the inverse function, or the multiplicative inverse function. Although some people might argue with me that inverse function is a bad name for this. It is the multiplicative inverse function, really. But I usually just call it the inverse function. And then, or the reciprocal function, whichever you want. And then the last one is the inverse squared function. And again, each of these has manipulations. So in other words, like the cubed root function, somebody might come along and say, oh, you know what? I'm actually looking at negative 2 times the cubed root of x plus 1, all that losing 18 or something like that. When you rip away all the numbers, you're just left with the cubed root of x. So if you rip away the negative 18 and the positive 1 and the negative 2, you're just left with the cube root of x, which is really our prototype function. So that negative 2 is doing something to the prototype function. The plus 1 on the inside is doing something to the function. And the minus 18 is also doing something to the function, which we'll talk about in the next lecture. But for now, let's actually look at each of these specifically and talk about their graphs. First thing I want to mention as we go into looking more specifically at each of these is that I write them as y equals x, or y equals x squared, or y equals x cubed, even though it's really f of x equals x, and f of x equals x squared, and f of x equals x cubed. Recall that when you're dealing with functions, the symbol f of x, or the function notation, is a stand-in for the letter y. So those two things really mean the same thing, so it doesn't matter that I'm writing y equals x here. Now what I'm going to do, I know you know how to graph this. This is actually a line. In fact, there is no need for a table here. This is a line, y equals 1x plus 0. It has a slope of 1 and a y-intercept of 0. In fact, 0, 0. So I could use that actually to graph this line. So let's go ahead and do that. I'll plot in red 0, 0, and I'll use the slope to get to the next point. The slope is just 1, which means I rise 1 when I run 1. So there's my second point, and I'll connect those points to create a line. There we have, that's the prototype for all linear functions. It's just the diagonal function here, or the base function. One thing I want to mention as well is that each of these functions has what I call an anchor point, and usually that anchor point will be the point that goes through the origin. So we'll talk about why I call that an anchor point later on. But it's essentially, if I'm going to move this graph left, right, up, down, doesn't matter, I'll grab that anchor point and just move that, and that will move. That'll be my handle to move the graph for later on. Our next prototype is the squaring function, or the quadratic function. And we already know actually how to graph this one, but I'm going to go ahead and plot some points anyway. I'm going to let x equal, let's say, a negative 2, a negative 1, 0, 1, and 2. Generally, when you're plotting points, or in other words, making a table of values, which is the weakest method to graph, we'll learn the best method soon. But generally, when you're making a table, you have to list out several points, and you try to be kind of symmetric about the origin, but often that doesn't help out. Even that doesn't help out. It only works with prototype functions. But once you get beyond the prototype functions, there's no real rule as to what the best points are to select. But in this case, we're dealing with a prototype function, so I'm just going to make my selections for x be symmetric about the origin. So let's see, when I plug in a negative 2, I'll get 4. When I plug in a negative 1, I'll get 1, 0, 1, and 4. So let me plot these points. And you see that we get a graph that is the parabola. That's the standard parabola. And again, I'm going to label that point at the origin as my anchor point. That's the point that I'm going to grab onto as a handle whenever I want to move this graph left, right, up, or down. I'll just move that point, and every other point will kind of move with it. Notice it's implied that you know how to obviously evaluate a function at a specific value, that you know how to plot on a coordinate system here. All these things are assumed. So I'm not going to review any of that in this lecture. Also, it is assumed that each one of these prototype functions, you know what they look like. So when somebody says what does y equals x squared look like, you should know immediately that, oh, it's a parabola, the standard parabola that opens upward. You should know how to graph that and make a perfect graph of it and label points accordingly. Now on to the cubing function. Again, I'll select points that are symmetric for x, that is, that are symmetric about the origin. Or symmetric about 0, I suppose. When you plug -2 in for x, you'll get y equals a -8. Plug in a -1, you'll get a -1, then 0, 1, and +8. And now I'll go ahead and plot those points on my Cartesian coordinate system here. Here's a rough sketch of the cubic function here. Please note that this point down here is -2, -8. My handwriting's not the best, but it is a -8, that is. And notice that it is a smooth curve, that it climbs and climbs and climbs as x gets larger. In other words, when x gets to like 3 or 4 or 5, this graph is far beyond the limits of this screen. It's way far up there. But it keeps widening out. That's definitely for sure. No matter what I plug in for x, there'll be a y value. It just keeps widening and widening out, but it's extremely tall at that point. Again, that point right there, the origin, will be my anchor point, the handle for this when I want to move it. And I can't think of anything else to really say about this one. What I might do is I might switch to graph paper on the next page just so that I can get my points exact here. Our next prototype function is the square root function. It's a very interesting function. One thing you should probably note here is that you cannot plug in negative values for the square root. Now, some people have this confusion about square roots because they have learned something about complex numbers in the past. And I have talked in my lectures about complex numbers as well. Complex numbers are numbers where you can take the square root of a negative number. They actually exist. They're unfortunately named imaginary numbers, but actually they do exist. The issue is that the x-axis and the y-axis, both axes, are only defined for real numbers. In other words, this x-axis is a list of real numbers. It's the real number line. The y-axis is also a real number line. There are no imaginary numbers on these axes. So we cannot have a negative square root occur on this, the square root of a negative number occur on this axis. So we can only plug in values that are either 0 or positive. So like x equals 0 is perfect. X equals 1 is another perfect number to plug in. X equals 2 is perfectly fine, but I don't know the square root of 2 very well, so I'll put 4 because I happen to know what the square root of 4 is. And we'll do 9 as well. I can get more fancy than that, but square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. And let's go ahead and plot those points. And as you can see, when I plot the points and I connect them, it almost looks like half a parabola on its side. Remember, a parabola, and I'll just quickly draw it over here, a parabola looks like this, but imagine that I didn't draw the right-hand side of that, and then imagine that I took that and spun it on its side. That's what we would end up with, is this picture right here. So that's kind of a neat idea that you can kind of cling to when you're doing the square root prototype graph. It really is just half a parabola on its side. And remember, it's the positive values because, first of all, you can only plug positive values into a square root, so it's only going to accept positive values for x. And it only returns positive values, right? The square root of a number is only going to be positive, well, possibly 0, right? In fact, that brings up a good point. Maybe I should have mentioned in the previous graphs what the domains and ranges were. So maybe I'll hop back and then pick back up in this one. It's pretty obvious actually with each of these what the domain and range are. Remember, the domain is a set of all possible values you can plug into a function. Well, if you look at this function, listen, I can plug in this x value, it leads to an output, right? I can plug in this x value, it leads to an output. I can plug in actually any negative x value I want, all the way up to negative infinity. Remember, you can't touch negative infinity, so it's just a parenthesis on it. And then as far as positive x values, I can plug in that one. I can plug in this x value, it leads to an output, and so on and so forth. I can keep plugging in higher and higher x values, and I can plug in anything I want. So it goes all the way up to infinity. And again, you can't touch infinity. As far as the range is a set of all possible outputs. And if you look at this function right here, you see the heights. I can get at this height, this height, this height. It can keep going lower and lower and lower. The same thing for how high this graph can go. No matter where I mark on the y-axis, I could hit the graph as I draw a horizontal line. So the range is negative infinity to positive infinity. You can think of the range as just all the possible y values your function can take. And here it could take any y value I want. In the parabola, that has kind of a unique domain and range. Well, maybe not a unique domain. I should write the word domain, not just D. The domain here, actually, I could plug in any x value I want. Remember, that's what you're asking when you're asking about domain, is what x value can I plug in. Any of these x values are possible. If I plug in this x value right here, it'll lead to a y value, but the y value will be off the screen, but that's still fine. So I can plug in anything I want for the domain. And if you look at the prototype function here, it just means, can you imagine plugging in negative 1,000 for x? Sure, it'd be negative 1,000 squared is the y value. So there you go. The range, on the other hand, is limited in this case. How low is your lowest y value for this red curve, for this parabola? You can see that the lowest point is that anchor point, actually, at 0, 0. So the lowest height I'll reach is 0. But from that point, I can get any y value I want above that. Any of these y values has the graph at that height. So I can keep growing and growing and growing. So that has a limited range. Still an infinite range, it's just that it doesn't go to negative infinity, it only goes down to 0. The prototype function for the cubic actually is not limited. The domain, I can plug in anything I want for x. In fact, often I tend to not look at the graph for the domain. I tend to look at the function itself and just ask, can I plug in anything I want for x? The answer is yes. So it means domain goes from negative infinity to positive infinity. The range, on the other hand, I usually look at the graph itself and I kind of interpolate or extrapolate. I look at the graph and I just ask myself, does it look like it's going to keep growing and getting higher and higher? Sure does. Does it look like it's going to keep getting lower and lower? Yep, it sure does. So the range, to me, looks to be negative infinity to positive infinity, and it actually is. Now we're caught back up to our example where I recognized that I needed to talk about domain and range. The domain of the square root function is limited because we cannot plug in negative values. None of these values back here have a corresponding y value. So the first x value I can plug in, the lowest x value I can plug in, is actually 0. And I can include that point, that's why there's a bracket there. But from that point, I can plug in any other x value I want. I can plug in 1 billion if I wanted to. I could take the square root of 1 billion. So the domain will continue to climb forever and ever. The range, on the other hand, has the same issue. The lowest y value that this curve attains is 0. It's the lowest height, and it actually reaches that height. After that, it will keep climbing. It'll reach any of these y values that I'm kind of marking out here. It just might take a while to get there, but it'll reach there eventually. So it'll climb off to infinity eventually. Now we reach the cubed root function, and the cubed root function is kind of the oddball of the group as far as what we've talked about so far, because Generally, in an elementary algebra class, a lot of instructors don't concentrate a lot of time on the cubed root. So we're going to spend a little bit of time talking about cubed roots first, and then we'll build this prototype function. The first thing I have to mention is that the cubed root of a number equals something means that b cubed must equal a. That is, like the cubed root of 8 equaling 2 means that 2 cubed is equal to 8. So essentially, when you're looking at the cubed root of a number, you're asking yourself, what number do I have to raise to the third power to reach that? What number would I have to raise to the third power to reach 27? Well, let's see. You usually start with very low numbers. When you start getting the cubed roots and fourth roots and stuff like that, don't go crazy. Don't think like, is it 9 or something? Don't do that. Start with low numbers like 2. 2 times 2 times 2 is 8. That's not going to work. 3 times 3 is 9 times another 3 is 27. So, the cubed root of 27 has to be 3. Now, unlike square roots, cubed roots, you can actually have negatives on the inside of as a radicand, basically. And so, in this case, you're going to ask yourself, what number would I raise to the third power to be a negative 125? Guaranteed the number will be a negative number. Okay, that's because a negative times a negative is going to be positive. Times one more negative will turn it into a negative. So it's going to definitely be a negative number. And then you start asking yourself, is 2 cubed equal to 125? No. Is 3 cubed equal to 125? No, we just tried that. 4 cubed is actually not 125 as well. 5 cubed is 5 times 5, which is 25, times another 5, which is 125. So this works out. The cubed root of a negative 125 is a negative 5. And again, that's because a negative 5 cubed is actually a negative 125. And notice, by the way, that when I cube negative 5, I put parentheses around the whole thing. It's because I'm cubing the entire number, negative 5. All right, let's try another one. And this one might not be so apparent to you. Let's look at the cubed root of 0.064. In fact, let's just keep it this way. Now, one thing that I do generally when I'm looking at a number when I'm taking the square root or the cube root of a decimal number, is I ask myself first, what's the cube root of 64? I'm going to see if I can do that. If I can do that in my head or without a calculator, then I might be able to do this one down here in my head or without a calculator. So let's see. Cube root of 64. What number to the third power becomes 64? It's definitely not 2 or 3, and it's not 5, because we've already talked about those three. 4 times 4 is 16, times another 4 is actually 64. Okay, so 4 to the third power is 64. That works out. So after I determine that the cube root of 64 is something I know, then I'm going to see, well, how do I get 0.064? Well, it's likely going to be either a 0.4 or a 0.04 or a 0.004. And your best bet is actually to start with the easiest one and work your way to the hardest. So in other words, start with this 0.4 first. And if you think about it, well, I'll go long-winded on this. 0.4 times 0.4, well, you know 4 times 4 is 16, and you have 2 spaces to the right of the decimal here, so you should have 2 numbers to the right of the decimal there. And then, of course, if you're going to cube that 0.4, it's 0.16 times 0.4. I know 16 times 4 is 64, and I have 1, in fact, let me highlight that. I have 1, 2, 3 numbers to the right of the decimal place, so therefore I should have 1, 2, 3 numbers to the right of the decimal place here. So this number should be, so in other words, 0.4 cubed should be 0.064. And I see, aha! This number, what number would I cube to get 0.064? Is 0.4. That's generally how I do it. I don't like to memorize rules and, if there's this many decimal places, I do that. I literally just say, can I take the cube root of 64? If I can, then I'm going to start looking at whether it's 0.4, 0.04, or 0.004. trust me, you won't have to go very far. It's usually within the first or second guess that you get the right answer. Now, often you'll get a number like the cube root of negative 3.8 or something like that. If you're given some type of cube root like this, first of all, I look at 38 and ask myself if I could take the cube root of 38. I already know I cannot take the cube root of 38. I get rid of decimals and negatives to see if I can take the cube root first. But I don't know anything that when raised to the third power will turn into 38, so I give up on that hope, and I know I'm going to grab a calculator. So just as a reminder of how to use your calculator, if you have a graphing calculator, if you're going to take the cube root of a number, there's a couple ways to do it. You have something under the math menu here, and this is not actually how I would do this, but you have an option under the math menu to take a cube root. It's the fourth option there. And it says, oh, the cube root of, and you want a negative 3.8, not a minus 3.8, but a negative. Remember, that's the negative sign, 3.8. And then close the parenthesis, and then you can hit enter, and it'll tell you. I'm going to go ahead and round this to the nearest hundredth place. So I'll say that this is going to be a negative 1.56. Now, if you want to know another way to do this without any justification, which is very unfortunate, usually you want to justify every step you do, you can start a parenthesis and say negative 3.8 and end your parenthesis, and you can raise that to a power. Now, it turns out that square roots are powers, and cube roots are powers, and fourth roots are powers. We really haven't talked about it, but it is true. It's the 1/3 power. So I can raise this to the, start a parenthesis for the power, 1/3 power. I'm going to hit enter, and then I'm going to describe a few things here. The reason why I use parentheses so much is because if I don't, first of all, the first set of parentheses on the negative 3.8, if I don't use parentheses there, it's only going to raise the 3.8 to the 1/3 power and not the negative 3.8. So I have to actually encase the whole negative 3.8. Won't make much of a difference in this problem, but for other problems it will. The power, the exponent, I have to put in parentheses because if I don't, what if I had written it like this? Let me write it out. Negative 3.8, and then if I just said raised to the 1/3, what the calculator is going to do is follow the order of operations. It's going to raise negative 3.8 to the first power. Then once it's done calculating what negative 3.8 to the first power is, it's going to divide that answer by 3. And you get that, which is a completely different number. So you have to enclose your exponents. If there's some operations going on, you have to enclose your exponents in parentheses. And again, just to reiterate, something that you might have recalled from another course or something like that, but the cubed root of a number is the same thing as that number raised to the 1/3 power. That's a topic we'll talk about later on, though. Not necessary right now. And now that we've gone through that entire conversation, let's go ahead and build our graph for our prototype function y equals the cube root of x. In this case, I'm going to choose values for x that are nice and easy to take the cube root of. We've seen a few of them here. I'm going to choose values like, let's see, I know that I could take the cube root of 0, I could take the cube root of 1, I could take the cube root of 8. So why don't we do that? Negative 8, negative 1, 0, 1, and 8. The cube root of negative 8 is a negative 2. Cube root of a negative 1 is a negative 1, 0, 1, 2. And I will go ahead and plot those points. And as you can see, I have connected these points up. It's a little bit tough to graph these by hand, but that's the look of the cubic function, or the cube root function, which actually kind of does look like a cubic function, kind of flipped it on its side. You should know this, practice building this by yourself, whatever. A few things to mention here. Domain. Turns out, just by looking at the graph or looking at the function itself, I can plug in anything I want for x. Anything my heart desires. So anything for x works. As far as the range, I can get any output. This graph keeps climbing and climbing and climbing as time goes on, ever so slowly, but it does, and it keeps falling as time goes on. So the range actually goes from negative infinity to positive infinity as well. Our next prototype function is the absolute value function. And again, I want to maybe take a little bit of time to talk about what an absolute value is technically. A lot of students have a misconception about the absolute value. They think that it just turns things positive, and that's a dangerous way to think of the absolute value. Technically, the absolute value splits you into choices, really. The absolute value of a number x is equal to the number itself if that number was positive to begin with, or possibly 0. Otherwise, it turns it into the opposite of that number if that number was negative. Now you might think, well, doesn't that just mean that it turns things positive? For example, like the absolute value of 9. Since 9 is positive, right? 9 is greater than 0, then this would just return 9. And if you look at the absolute value of a negative 5, well, since a negative 5 is negative, it will turn it into the opposite of negative 5, which would be a positive 5. So with numbers, it is true, actually, with numbers, that it turns it into a positive. But that's only numbers. When you're dealing with variables, something completely different happens. So like the absolute value of 3x minus 4. I've seen too many students write this as 3x plus 4, but that's not what it is. There's two possibilities here. It's either, well, 3x minus 4 if 3x minus 4 is greater than or equal to 0. Otherwise, it's the opposite of 3x minus 4 if that 3x minus 4 was less than 0. In other words, in this first case right here, if you solve for x, you'll get that, well, let me erase it. If you solve for x, you'll get that it's 3x minus 4 if x is greater than or equal to 4/3. Otherwise, it's equal to the opposite of 3x minus 4 if x was less than 4/3. So that's kind of an important point to make. A lot of students get this stuff wrong. So it doesn't really hurt us or help us here in this situation, but I just wanted to mention that as an important side note before we move on into graphing this absolute value function. Let's go ahead and just pick some easy values here. Now we're just going to go back to this easy idea of the absolute value, which everybody loves, which is that it makes things positive. So I'm just going to choose symmetric values for x here and find out the symmetric outputs. And then I'll go ahead and plot these points. And what we get is a beautiful V-shaped curve. Well, it's not really a curve. Technically it is a curve, actually. But we get a V-shaped object. One way that I've often remembered this when I was a student is that this is almost like a line. Y equals the absolute value of x. It sort of looks like y equals x. It's just that instead of that line continuing on down this direction, the fact is the absolute value forces all my y values to be positive. So they reflect themselves up here and go in this positive direction instead. But that might be a little too technical, and some people might not be as conceptual, but that is technically what's going on here. The domain of this, I can plug anything I want in for x. The range of this, in other words, the set of y values that are the outputs, well, you can see it can only go down to 0. So I can go all the way down to and include 0. And then it goes off to infinity. It keeps climbing and climbing. And finally, the last thing I want to mention is that we do have an anchor point here. It's at 0, 0, anchor point. And I didn't mention it in the last graph with the cube root or the square root functions, but 0, 0 are also the anchor points for those functions. Now we're on to the last two prototype functions. We have the inverse prototype function and then the inverse squared prototype function. And both of these are going to involve a kind of a lengthy conversation about their development. First part is not going to be so bad. We're just going to plug in values. I'm going to plug in a few values actually. I'm going to plug in maybe a negative 5, a negative 4, a negative 2, negative 1, 0, 1, 2, 4, and 5. The reason why I'm trying so many points is because this is a very interesting graph, and it might take a little bit for us to design. If I plug a negative 5 in for x, I'll get a negative 1/5 out for y. And then if I plug in a negative 4 for x, I get a negative 1/4, and then a negative 1/2, a negative 1. But then when you plug in 0, it's undefined. Remember, division by 0 is undefined. And I plug in a 1, 1/2, 1/4, 1/5. The reason why I plug in so many values, actually, to be honest with you, is just to get an idea of the long-term behavior of this graph and to also have enough points that I can graph it properly. I highly recommend, if you're going to graph this by hand, to choose your scales very carefully. It looks to me as though if I choose my y value scale to maybe go in fourths or fifths maybe, that it might be a little bit better to work with. So let me go ahead and set up my y-axis and my x-axis accordingly. Okay, I also scooted the graph over slightly just to make more room. What I actually decided to do was do these in lengths of, or hash marks of 1/4. So this is 1/4, 2/4, 3/4, 4/4 is the height of 1, then it continues on. And so let's go ahead and plug in these values. Now, when x is a negative 5, way out here, y is a negative 1/5, which is just slightly less than negative 1/4. So I'll mark that on here, and it's going to run into my lettering, so I'm going to move the lettering too. So I moved the numbers up above, and then I went ahead and labeled negative 5, comma, negative 1/5. Negative 4, I'm at a height of a negative 1/4. There I go. I had to move things slightly again just because I was off the grid. Negative 2 leads to a negative 1/2, so that's a negative 1/4, and negative 1/2 is right there. And negative 1 leads to a height of negative 1, so that would be right about here. 0, we said we're undefined, and then all of a sudden at 1, we're at a height of 1. So all of a sudden we skipped sides for some reason, and 2, we're at a height of 1/2. Oops. There we go. And then 4, we're at a height of 1/4, and 5, we're at a height of 1/5. Now, in this case, it might be better to find out what happened between negative 1 and positive 1. In other words, plot a few more points there. So what I'm going to do is plug in a couple more values between negative 1 and positive 1. Like, let me just build an extra little table here. Like negative 1/2, and negative 1/4, and then 1/4 and 1/2. Just to see what happens for those x values, because for some reason this graph just doesn't look right. Well, if you plug in a negative 1/2, you'll have 1 over a negative 1/2, which is the same thing as 1 divided by a negative 1/2. And remember, division is, you could change that to multiplication by taking the reciprocal of the second fraction. Oh, I see. So when I plugged in a negative 1/2 for x, I get a negative 2 out for y. If you do the same math and plug in negative 1/4 for x, we get a negative 4 for y, and then 4, and then 2. So plotting these points, when x is a negative 1/2, which is right here, the y value is a negative 2. And when x is a negative 1/4, which is right here, the y value is a negative 4. So let me go all the way down to negative 4 here. So it's negative 3, 1, 2, 3, about here, even though my graph is still skewed slightly. And same thing on the other side. When I'm at 1/4, I'm at a height of 4, so it's 3, 4, right up here. And when I'm at 1/2, I'm at a height of 2. Let's connect these points and see what this curve looks like. That's a very interesting curve, and actually brings up a few things to talk about. First thing is that these at x equals 0, our line or our curve is undefined, right? We cannot plug in 0 for x. That brings up a very, very special concept in mathematics, the concept of an asymptote. Let me draw it on there first, and then we'll talk about really what it is. So we have this vertical dashed line. We usually use dashed lines for asymptotes. So we have this vertical dashed line that that our graph cannot exist on. It's because at x equals 0, we are undefined. Our graph here is undefined. So this is known as a vertical asymptote. It is a vertical line which the graph cannot cross. And I'll go into a more technical definition of it later on in my lecture series, but for now it's just good enough to know that a vertical asymptote is a vertical line that cannot be crossed at all. Well, I mean, it can be crossed, but it can't be touched by your curve. And in fact, if you notice, it acts almost like a magnet. As those red curves try to approach it, they bend away from it. It's not that they bend back upon themselves. They still have to be functions, so they still have to pass the vertical line test. But they bend, they still climb and climb and climb, and they get really close to that vertical asymptote, but they never touch it. The second concept that this brings up is the idea of a horizontal asymptote. A horizontal asymptote is somewhat like a vertical asymptote, but somewhat not like a vertical asymptote. Horizontal asymptote really describes the behavior as x gets really large or really negative, really large in the positive direction or really large in the negative direction. But it's called a horizontal asymptote. And for now, all that you need to know is that a horizontal asymptote is just a line that describes the behavior of the graph as x gets really large, either positive or negative. And by the way, when I'm graphing this graph, oddly enough, my anchor point usually is the origin again. A lot of people don't use the anchor point as the origin, but in this case, or for this function, but I use the anchor point as the origin because when I'm going to move this graph left or right or up or down, I'll grab where these horizontal and vertical asymptotes cross, and I'll move them left, right, up, down. Now, as you look at this, you'll notice a few skips in the domain and the range. The domain looks to me as though I could plug in any x value I want all the way down to negative infinity, but as I climb, all these x values are okay all the way until 0. I cannot plug in 0, so I have to not include 0, so that means I have a parenthesis. But then I get to skip over it. In other words, you're going to glue onto that or union onto that another interval and start at 0 and go on to infinity. So my domain includes basically all numbers except for 0. That's what that unioned interval notation means. The range, look at the red curve, the range can fall all the way down to negative infinity. Your graph falls all the way down to negative infinity, and it climbs, as far as heights go, climbs all the way up to 0, but it actually never reaches a height of 0. So I'm going to put a little parenthesis on there. Some students will ask, and it's a great question, why doesn't it reach a height of 0? It looks like it'll eventually climb up to this horizontal asymptote. Is it that we cannot touch a horizontal asymptote? No, it's not that at all. Vertical asymptotes you cannot touch. Horizontal asymptotes, I never said such a thing. Horizontal asymptotes you actually can cross. It does happen every once in a while that a graph will cross a horizontal asymptote. So how do I know that at some point that's off this screen that these curves do not cross the horizontal asymptote? Now, good question, Roy. I'll tell you why. It's because if you look at the function itself, 1 over x, the only way for a number, a fraction, to turn into 0 is if its numerator is actually 0. That's the only way for a fraction to turn to 0, is if that numerator is 0. But that numerator is 1. It's not 0. That numerator will never be 0. So there's no possible way for that fraction to become 0. Okay, so there's no possible way for that y values to become 0. So the range cannot be 0. By the way, your y values climb from negative infinity all the way up to 0, but not including it, hops over it, and then starts at the other side of 0 and climbs all the way up to infinity. This is a very unique graph, and it's probably, honestly, one of the focuses of more advanced courses in college algebra, and I will actually focus lectures on it in the future as well. So now that we've done all of that, this one will actually not be as bad because we know how the setup will go. I'm not going to choose such, well, maybe I will choose like -5, again -4, a -2, a -1. Now I'll go ahead and do a -1/2, a -1/4. We'll try 0 again, but I know we're going to be divided by 0, so that's actually undefined there. There's no point in actually have tried that point, but that's okay. 1/4, 1/2, 1, 2, 4, and 5. I'll extend this down. Now, when I plug in -5, I get 1 over -5 squared, or in other words, 1 over 25. When I plug in -4, I get 1 over a -4 being squared, or in other words, 1/16. You see, these are much smaller numbers, and they're positive. Plug in -1/2, I get 1 over when I plug in -2, I get 1 over -2 being squared, which is a positive 1/4. Plug in a -1, I get 1 over a -1 squared, which is 1 over a positive 1, which is 1. And then when I plug in a -1/2, I'm going to show this mathematics actually. So when you plug in a -1/2, you get 1 over a -1/2 being squared, which is basically 1 divided by 1/4, right? The -1/2 squared is just 1/4, which is 1 times 4 over 1, which is going to be 4. And you can do the same math to find out that that will be 16. This will be 4. Oops, not 4. This will be 16. This will be 4. This will be 1. This will be 1/4. This will be 1/16, and then 1/25. Now I'll go ahead and plot some of these points, not all of them, because I don't have a height of 16 on this curve on my grid here, but I'll plot some other points. This has somewhat of the same look as the last function we graphed. We know that we cannot plug in x equals 0, so that's going to present the same issue that we had in the last graph, which is that we'll have a horizontal or a vertical asymptote. So let me go ahead and mark that in there. That's just that vertical line, again, that the curve cannot touch. And as our curve approaches from either side, from the left or from the right, it bends. In this case, both sides bend upward. And recall, in the last case, one side bent upwards, the other side bent down. That was the nature of that prototype function, just the inverse function. This, that they both bend up, is the nature of the inverse squared, the 1 over x squared function. And now, let's talk about the horizontal asymptote. Remember, that just determines the behavior of the curve as x gets really large. In other words, as x gets really large, that red curve will want to approach the horizontal asymptote. And again, as x gets really negative, the same thing. The curve really wants to get close to that. It gives us a great idea of how the curve looks over the long haul. Again, I have an anchor point that I have where the asymptotes cross. So I use that anchor point to help me move this graph or this curve left, right, up, or down. And I have a domain and a range that I can talk about. The domain is everything except for x equals 0. In other words, I can have any x value from -infinity all the way up to 0, but I have to not include 0, so I have to hop over 0 and continue on towards infinity. Same thing can be said for the range, actually, except the range in this case is very unique. I cannot have negative y values. You don't see any curve in the negative y value area. Basically, quadrants 3 or quadrants 4, you don't see any curve down there. So, My range starts at 0. That's the lowest value my curve can take, and it cannot actually take on the value of 0. Remember, this is a fraction. The only way a fraction can turn into 0 is if the numerator itself is 0. In this case, the numerator is actually 1. So this fraction can never attain the value of 0 itself. So the range starts at 0 but doesn't include it and climbs on up forever, as you can see in the middle of the curve. Now, those are all the basic graphs that we're going to deal with in this course. However, the same setup is done when you're building basic graphs in trig or calculus or something like that. There's not very many others, to be honest with you. Oh, we do have one more we'll approach in this course later on, and that's an exponential, two more, exponential and logarithmic curves. But same idea. We're going to build a table of values and plot some points and look at what the curve looks like. And then you just need to know that those curves look like that from that point forward, or you need to be able to quickly rebuild these base graphs. If you build them a few times by yourself, as you're going through and practicing problem sets or something like that, you'll get used to what these curves look like. You'll start kind of looking at the functions and going, oh, that's that one that's always positive and avoids the y-axis or however you think about it.